Welcome to Ushendra's engineering tutorials. It's all about how a basic meter can be used as a voltmeter. Here we go. This is how a basic meter looks like. The layout, not the inside construction or anything, the layout of a basic meter. So here, the voltage to be measured is connected over here. And remember, the pointer deflection is due to the current flowing in the circuit, which is directly proportional to the voltage we are measuring. The deflection of the pointer is due to the current only, but the scale will be indicating the voltage which we are measuring. For example, like it's a 10 volts over here, which may give rise to some 2 amperes current, or it may be 7 amperes current. The pointer may be over here, or randomly the pointer may be over here. It doesn't, the scale of the basic meter won't indicate the current, but this position will be marked as a 10 volt for supposing. Like, let's reduce the current to some 6 volts. So even the current reduces, the current flowing through the circuit reduces. That may be, for supposing, that may be some 4.5 amperes for supposing. So previously it was 7 amperes, and so the pointer was here, and that position was marked as a 10 volts, which was the voltage to be measured. And here in this case, like 4.5 amperes, the pointer would maybe somewhere else over here, and that's marked as a 6 volts, like that. Remember an important statement: the deflection of the pointer of the basic meter is due to the flow of current, which is directly proportional to the voltage which we are trying to measure. On the other hand, while this designing a voltmeter, etc., while in range extension, we have another important parameter to be taken into account: the maximum amount of current the basic meter can handle. IFSD, remember IFSD in some textbooks, and it's a meter current IM meter. The maximum amount of the current the basic meter can handle, IFSD, full scale deflection current, the maximum amount of deflection here. Beyond that, if the current passing through the basic meter exceeds this IFSD, it undergoes throttling and the mechanical arrangement gets damaged. So proper care has to be taken that the current flowing through the basic meter doesn't exceed this IFSD. And another important statement to be remembered in this context, like, we don't need a series resistance. Here I seriously stress on this point: unless and until the current in the loop, in the circuit, isn't exceeding this IFSD, we don't need a multiplier resistance, a series resistance. Yeah, it's short for sure, right? So you may have seen while designing, you will come across a series resistance RS. We don't need this series resistance unless and until the current does not exceed this IFSD. So there may be a increase in the voltage to be measured, for supposing 50 volts, and this is capable of, it's like 6 volts. It may produce some 2 amperes, which may be in the range of the basic meter. This 2 amps may be the IFSD of the basic meter. Then we don't need to insert a series resistance, right? 6 volts may give rise to a 2 ampere. And what if the 2 ampere is equal to the full scale deflection current of the basic meter? Under that circumstance, we don't need a series multiplier over here. Once this unknown voltage exceeds, let's suppose it may be, we have changed the input voltage to 50 volts. That may give rise to some, for supposing, that may give rise to some 15 volts. Then we are in need of a series resistance like this one. This limits the current. Okay, so we need to have a series resistance over here. Now this one, it's also known as a multiplier resistance to limit the current. So this may be like, this may limit to the 50 volts. This may 50 volts giving rise to some current, total current in the circuit. That may be the value of the series resistance should be selected in such a way that this current limited to the full scale deflection current. That's the point. What if it may be like 40 volts? It's reduced to 40 volts from 50 volts. So that will reduce the current even. So the deflection would have been somewhere else here. So this, it may like 40 volts. Now this position of the basic meter is denoted as 40 volts, like that. Okay, the deflection of the pointer is due to the current only, but that current which is directly proportional to the voltage which we are measuring. And with all these discussions, believe me, yet another important term, parameter, whatever you call, comes into the picture. It's a sensitivity of a voltmeter while extending the range of voltmeter to different ranges. For supposing 0 to 10 volt 0 to 10 volt range voltmeter has to be extended to 0 to 50, 0 to 100, 0 to 1000. It can be making use of a proper series resistance, multiplier resistance. We can extend the range of a voltmeter to any level which we want. And a very important parameter to be comes into the picture with all these discussions. It's the sensitivity of a voltmeter. What it is, you will come across while in designing sensitivity of a voltmeter S. Very important factor. It's nothing but sensitivity S is defined as the reciprocal of full scale deflection current IFSD. Guys, a very important one. I'm marking with red, so understand the importance of this one while designing its for sensitivity. It's defined as the reciprocal of the full scale deflection current, right? And it may be like we may be in need of designing a 0 to 50 volts range voltmeter, for supposing, right? Under that condition, and yes, another important parameter to be mentioned, the internal resistance of the basic meter, RM. That cannot be neglected. The discussion would be incomplete if we don't include this one with when the discussion comes about full scale deflection current. Now what will be this? It's a current, and that can be written as a ratio of voltage to resistance, I guess, if I'm not wrong, right? So this can be 1 upon full scale deflection. It's a current. Full scale deflection, it's a current, but this can be written in terms of voltage and something. What is that something? So V upon what? V upon RM. This is the current through the basic meter, right? So what current? It's a what resistance? It's a RM, the internal resistance of the basic meter. Make a note, you may be confused. And what is this? What will be this? This will be that the highest range on the scale which we are seeing. It may be like 50 volts. Now this 50 volts will be this one, this will be this, and RM will be the internal resistance of the basic meter. So this takes another form here. S will be equal to what it is? It goes up, so it's RM by V. Once again, RM being the internal resistance of the basic meter and V being the maximum range voltage, right? And so in that case, even yet another important parameter comes into picture. What will be the units for this one? Guys, this is for you, like it's a short answer question, like it means RM ohm per, it's a volt, ohm per volts. Very important parameter. What may be the, you may have a simple question, what are the units of a sensitivity of a voltmeter while designing? What is the unit of a sensitivity of a voltmeter? Ohm per volt. Very important one actually. Yeah, and so I've rounded in red, right? This knowledge is important, and we cannot insert whatever RS value we want. That has some it sticks to some conditions and something like that. So what it is, this 50 volts may give rise to flow of IFSD. So now it's a voltage, okay? So no, we don't know the value actually. So for the discussion to be easy, I took the numerical, but let it be volt here, let it be volt over here. giving rise to a full scale deflection current IFSD, which is in the range of the basic meter, right? And here what according to Thevenin's theorem, Thevenin's application, this volt is equal to this volt plus this volt, and IFSD is flowing in the circuit, right? So that will be equal to V, which is equal to what? IFSD into RS, okay, into RS plus IFSD RM. And I guess we are in search of this RS. Here we are in search of this RS. So RS will be IFSD, RS in this case IFSD, RS will be equal to pushing this one which is in the RHS to this side. This will be V minus IFSD RM, right? And we are in search of this RS, so RS will take the form, will be V upon IFSD minus IFSD upon IFSD gets cancelled, and we are left with RM, right? This is the expression for RS. The voltage, the maximum voltage the basic meter is to be designed for, and the full scale deflection current and the internal resistance of the basic meter. Hey guys, another small transition over here. What is this? 1 upon IFSD? That one, 1 upon IFSD is equal to this. So this takes another, this equation takes another form, which is RS is equal to V as it is into 1 upon IFSD is the sensitivity S minus RM. Now this is the my another expression for, we'll have to make use of this and we'll have to make use of this also. It may be asked using sensitivity method design a voltmeter, then we have to make use of this equation. Both the equations are valid only, it's true, both the equations are valid, and I ask you to remember this one. A lot of numericals to be solved based on this one. It will be very easy if we make use of this equation while designing a basic meter as a voltmeter. And what if multi-range? It may be like when we go for a multi-range, another range of the discussion was for 50 volts, right? 50 volts. We are connecting over here, okay? So another range, let's go for 100. Let's go for 100 volts. We need to have another series resistance like this one that's connected over here. 150 volts, it's like here another, it's not the appropriate value, it goes on, increases, like this may be higher range, we may be having higher resistance like that, okay? So it's advised to start from the, while changing the range of the voltmeter, it's advised to come from higher level to the lower level. Please remember, make a note of this statement. And this is for multi-range. Another range, we may have another resistance like this one. This is the basic, but we have another design, more appropriate, more useful, more protective. It may be like this one. We have the voltage to be measured. It's RM. I'm not erasing it. It's RM, internal resistance of the basic meter. We have a string of series resistances like this one. Here, it's like this. Another one. Okay. So now this is the more appropriate, more protective. The voltage to be measured may be connected over here, maybe not. It's connected over here, and we have a switch arrangement with this one. So for one range, the highest range, it will be over here, and for the next lower range it will be over here, and for the next range it will be, the switch position will be taking this. For the highest range, R1, R2, R3. Now this is more appropriate designing of a multi-range voltmeter, right? So a small recollection, it's the full scale, unless and until the current produced by the voltage does not exceed the full scale deflection current, the maximum amount of current the basic meter can handle. We don't need an RS series resistance or multiplier resistance. It multiplies, right? Multiplier resistance. And once the current through the basic meter exceeds the IFSD, the maximum amount of current the basic meter can handle, then we have to go for a series resistance. As that happens when, as the voltage goes on increases, the range of the voltmeter goes on increasing. So please make a note here. Sensitivity, this is the equation, the ohm per volt, the units for the sensitivity being ohm per volt, and this is the final expression for IFSD. It has two ways, V upon IFSD minus Rm. The reciprocal of IFSD being the sensitivity, that can be written like this one also. Make a note please, very important equations. A numerical for a better understanding, the internal resistance of the meter is given being 100 ohms and the full scale deflection current 10 milliamperes. It has to be extended, a basic meter to be designed for a multi-range voltmeter like this one. Another comes into the picture, the first one being a lower range, this one, right? So under this case, the basic meter should be designed to measure 0 to 5 volts, and this is the series resistance we need. And full scale deflection current, how much? It's a 10 milliamperes. Under this condition, what is the total resistance of the circuit? What will be the total resistance? This is unknown, okay? This is unknown. So what will be the total resistance of the circuit? It will be V by I. So total resistance RT, here RT will be equal to this by 5 volts upon the full scale deflection current 10 milliamperes, and milliamperes, that will be kilo, and 5 by 10, that will be 0.5 kilo ohms. Now our total will be 0.5 kilo ohm or else 500 ohm for a beginner to understand, right? Now how to obtain the value of R3? When this is subtracted from the total resistance, then we will have R3. What is R total actually? The resistance R total, once again, R total resistance will be R3 plus Rm, right? And from that which we have, R3 is equal to R total minus Rm. R total, it's 500 ohm minus Rm being the internal resistance of the meter, it's a 100 ohm, which is equal to 400 ohm. So now my R3 will be this, which is equal to 400 ohm, right? And what is the second range? Another range, another resistance comes into the picture with R2, that will be, and the switch position will be over here, and what the second range? It's a 0 to, it's no more 0 to 5 volts, it's 0 to 50 volts, 50 volt range, right? And under that case, guys, I need this place. Under that case, what will be the total resistance? The total resistance RT, R total, will be equal to this voltage upon IFSD, in the sense 50 volts by much IFSD, 10 milliamperes, which is equal to, guys, this milli, that becomes kilo, and this is the case 5k or else 5k or else 5000 for a beginner, 5000 ohms, right? And what will be the total resistance now in this case? R total will be equal to this plus this plus this. It's a R2 plus R3, it's a 400 ohm plus 100 ohm. R3, value of R3, and the internal resistance of the basic meter, right? So from this R2 will be, it's a R2 will be, R total is that much, 5000 ohm minus 500 ohm, which will be equal to 4500 ohm or else 4.5 kilo ohm. This is my this is my value for R2. This is my value for R2, which is equal to 4.5 K. And what about R3? When going for the next range, what is the next range? Here now the switch position won't be here anymore. Small transition over here. third range. For the third range, this is the arrangement, and the switch position will be here. Like from the beginning we have stick to here. How much? It's a 100, 0 to 100, so 0 to 100 volt. Now what will be the total resistance? R1 will be, now the total resistance RT will be how much? 100 volts upon 10 milliamperes, so gets cancelled, we don't have this milli going up, that becomes 10k. This is the total resistance. Now we need R1. Subtracting R1 from this one, we'll have the value of R1. So R total will be equal to R1 plus 4.5k plus 0.5k, total everything, right? So it's R1 will be equal to R total minus 5k, which is equal to R total. Just now we have obtained 10k minus 5k, it's equal to 5k. This is the value of my R1. So this is my value, equal to 5k. This is my design for a multi-range volt. Guys, you try with the sensitivity method, we'll obtain the same results. Right? Hope you have understood this one. Remember, the full scale deflection current plays a major role in designing. Actually, we didn't make use of that. No. We didn't make use of that another expression. What was that? RS is equal to what is that? R total voltage range V into S minus R. We didn't make use of this one. You guys make use of the same way, same result, right? RS. Now hope you understood this one. So if you find it useful, please subscribe to Ushendra's engineering tutorials and support me with your valuable share. Thank you so much for being with me.